Dimension. So what is the dimension of a vector space? Something like, R4. You probably have an idea of what the dimension of that is. Dimension in the usual sense. But in the mathematical sense, we want to come up with a precise definition of what we mean when we say that the dimension of R4 is 4. What do we mean by that? So we're going to move towards a proper mathematical definition, which will coincide in the case of Rn with what we usually think of as dimension. Anyways, we're getting there. For now, let's move towards that definition. Okay, so if you have a basis of, say, n vectors, and then you consider a set with n plus 1, n plus 2 vectors, that set is going to be automatically dependent. Let's see in R2, this is easy to see, right? If I have 1, 2, 3, 4, 5, 6, that is, we've already seen that that's automatically dependent since, this matrix here does not have a pivot for every column. Not a piv for every column. Okay, so we can see in R2 how this makes sense. Okay, I have a basis. This is the so-called standard basis. This was sometimes called the standard basis. We have this standard basis. It has 2 elements. And you can see that if you have any set with 3 or more elements, it's going to be automatically dependent because of what I was talking about over here. Okay, the corresponding matrix is not going to have a pivot for every column. Okay, moving forward. Next thing is actually the clincher here. Okay, again, we're trying to define dimension in some sensible way. Now we're going to go a little bit further with this next theorem. What are we saying? We're saying that if you have a basis with 2 elements, then every other basis for R2 is also going to have 2 elements. So in R2, or let's say let's just do R2 again. It's easy to see. You have the standard basis. Let's call that B1. B2. You can have 2, 1, 0, 1, 0, negative 1. Why not? B3. Pi squared 1, E squared 1, 1. Why not? 10. Doesn't really matter. So what do I want to say? These are all bases. All bases for R2. But they're quite different, right? They look different, but what do they have in common? They all have 2 elements. Okay. Have exactly 2 elements. Okay, so what can I say here? So in R2, it's easy to see why theorem 10 is true. Because if you have more than 2 elements, then you are necessarily a dependent set. And if you have fewer than 2 elements, then you can't possibly span R2. Okay, so this 2 is our magic number here. Okay, and this number 2 is what we're going to call our dimension. Now, what are we saying? We're saying something about the number of elements in a basis. Okay, that is our dimension. Okay, not because you have vector spaces that consist of polynomials or matrices. Okay, you can't draw axes and say, oh, there are 3 axes, so 3-dimensional. You can't do that, right? But you can find a basis, and you can always find a basis and count elements. And that is what we're going to use as our definition of dimension. Okay, if you have vector space V, and let's say there is a basis that has exactly n vectors, then we will define the dimension of V, short formed as dim V. We'll define that to be this number n. So dimension is the number of vectors in a basis. That is our definition. And the theorems I just talked about, well, why did I talk about them? Well, I have to have a definition that makes sense, right? I have to be sure that this number of vectors in a basis, I have to make sure that's stable. Okay, I can't have, I hope you agree that the definition wouldn't make any sense if you were, for some reason, able to have a basis with 6 vectors and also a basis for 7 vectors. Okay, this definition would not be suitable. It would be, completely wrong. Okay, so, and we'll notice that this corresponds with what we think of as dimension in the case of R2, R3, R4, and whatnot. If you go dim R2, okay, you'll see that's obviously 2. Since we have the standard basis. I'm not sure if I mentioned standard basis. This is a very simple basis consisting of E1, E2. Okay, so this is a basis. It has 1, 2 elements, and therefore this dimension is 2. Okay, similarly, dim R3 is going to be 3. You can choose whatever basis you want. Okay, it's always going to have three elements. Okay, I can very quickly say that this is a basis. Why can I do that? Well, what you do is you look at this matrix 10. You write down the corresponding matrix. It's maybe the easiest way. So I look at this determinant. It's the product of the diagonal entries. Well, it's not 0, right? So columns are independent. So what do I want? Let's go back to columns are independent. How did I put this to you? If the determinant is non-zero, well, what it means is the matrix isn't invertible. So let's start over. Let's say that instead. So this matrix is invertible. So it has a pivot for every row. And for every column. Now, because it has a pivot for every row, that means that the columns span R3. And because it has a pivot for every column, it means the columns are independent. So this set is a basis for R3. Okay, that's my reasoning in red there. I've been doing this so long that I just wrote this down and barely thought about it, but my reasoning is a bit more involved there. Okay, when I say this, I'm referring to this set here. Okay, so our definition of dimension, this is a 3 here, our definition of dimension does correspond to what you would expect for R2, R3, R4, and so on. How about something like polynomials of degree at most 2? Well, let's get a red pen out again here. Okay, a very simple basis is you take 1 t and t squared. So the dimension of P2 is actually 3. So if you think about this in general, if I have Pn, that will be n plus 1. If I have Rn, it will be just n for the dimension. What about the dimension of the, let's say, 2 by 3 matrices? 2 by 3. Well, what I'm going to do is try to find a basis. Two rows, 3 columns. So, well, I'm going to do a kind of standard basis. I'm going to start with that one and just work my way through all the ij entries until I get here. It's a total of 6 elements. So dimension of M 2 by 3 is 6. Well, more importantly, it's 2 times 3. From this, we deduce that the dimension of the M by N matrices, that is M times N.